If you are going to develop a mmWave wireless communication system, the biggest challenge is fading, which includes large-scale and small-scale fading. To minimize the fading effect, especially large-scale fading, which is many path loss, the front-end system must have high directivity and good frequency conversion quality. The antenna array is a popular solution to achieve high directivity. And furthermore, beamforming is one of the most important and effective techniques. By using beamforming, the transmission angle of arrival can be electrically steered in different directions if needed. On the other hand, frequency conversion is a complex issue that you have to take into consideration. There are two main parts of frequency conversion, which are the local oscillator and the frequency converter. The most difficult thing is how to develop a good frequency conversion device. You have to pay attention to LO's quality, such as phase noise, harmonic, even the driving power of your frequency converter. Otherwise, control interface, synchronization, and regarding accessories are the things you have to pay attention to as well. How do we develop the mmWave wireless beamforming transmission? You can do this by using TMYTEK's BBox and UD Box. In this section, you will see a mmWave wireless communication demonstration based on 5G NR-FR2 protocol with 64 quad modulation and 100 MHz bandwidth. Therefore, you can conduct your research and development by using this architecture. First of all, here is the BBox. As we know, BBox is a single box beamforming device that allows you to control all the beamforming. Let's see how this works. We got the beam and we can control this device easily with our GUI. And then, here is the UD Box. UD Box takes care of all things you have to develop as an up and down converter, such as LO, control, synchronization, and frequency conversion. All you have to do is connect the power and Ethernet, connect the RF and IF signals, turn on the device, and control it on our GUI, which is TMX Lab Kit. Finally, the system is all set, and you have to check the system link for your situation. For system evaluation, some of the important parameters we should know, like free space loss, power budget, noise budget, gain budget, EIRP, and TRP. And finally, the system characteristics are usually based on SNR and EVM. In this section, we will demonstrate the 100-meter outdoor scenario. The most important parameter we are focusing on here is EVM. The lower value of EVM, the better transmission quality. Let's see how we evaluate the link budget in this case. At first, we put a 4x4 BBox and an UD box at the transmitter side. The input P1 dB of up converter is about 10 dBm and the input P1 dB of BBox 1 is about 5 dBm. The beamforming gain is controllable and the maximum EIRP is around 40 dBm with 32 degrees 3 dB beam width. The 100-meter distance free space loss is about 100 dB at 28 GHz. Next, at the receiver side, we have a 8x8 BBox and an UD box. And the beamforming gain of BBox is controllable as well. The maximum receiving gain is around 43 dB with 25 degrees 3 dB beam width due to 8x8 antenna array. And the input P1 dB of down converter is 10 dBm. Finally, we found out the SNR is too low to demodulate the signal at the baseband. Therefore, some gain block could be inserted at specific point to compensate for the free space loss and enhance the SNR. By the way, the 5G NR platform that we used here is NI-PXIe for both the generator and analyzer. Everything is all set. Let's see how it works. Enable the waveform generation with 5G NR-FR2 protocol and 100 MHz bandwidth. Enable the signal analyzer to demodulate the 5G NR-FR2 signal as well. Now we can see the transmission performance on the monitor. the EVM is around -25 dB now, which is not very well. In this case, we just use TMYTEK's amplifier between BBox and UD Box. Then we can adjust the beamforming direction for line of sight alignment and see if there is any better. Now, we can see the difference after beam adjustment. The EVM is better. The best performance is around -32 dB. In this mmWave transmission experiment demonstration, you can see how easy it was to develop and set up whole experiment by using TMYTEK's BBox and UD Box. As demonstrated previously, the EVM is around -30 to -32 dB at the distance of 100 meters, and maybe even further. Here is another application scenario.
Hi, my name is Malay and I'm a solutions marketer for wireless research at NI. With NI and TMYTEK's collaboration, we want to leverage the NI USRP platform and open protocol stacks to enable researchers to quickly move new concepts from mathematical models to over-the-air mmWave testbeds. TMYTEK's rapid mmWave prototyping solution comprises of the BBox 5G beamformer and the UD Box 5G, an ultra-wideband up and down converter that can cover the 5G FR2 mmWave bands. The mmWave solution can be paired with the NI X410 USRP, our latest and most powerful USRP yet. It has 4 transmit and 4 receive channels, and each can support up to 400 MHz of bandwidth. We hope the NI and TMYTEK's mmWave prototype system will enable wireless engineers to rapidly innovate and tackle some of the open challenges facing the commercialization of mmWave technology. Thank you.
If you want to conduct the channel sounding, spectrum monitoring, or wireless transmission quality test in the flesh, you are more than welcome to use TMYTEK's product in your experiment.